Okay, so example 3, picking up where we left off yesterday. Remember we had the guy in example 1 riding the Ferris wheel, good Precal student, started his stopwatch at the bottom. And then in example 2, I don't know if it was the same guy, but he kind of slacked in his responsibilities. He shirked his responsibilities and started his stopwatch completely at the wrong time. Well, in example 3, it's the same guy from example 1 and 2 from yesterday. Okay? We're giving him a chance to redeem himself after example 2. So the rider from example 1 and example 2 leaves the fair. He leaves the Canal County Fair, and he goes home. And what does he do? He constructs a perpetual motion machine. Holy moly, how do you do that? Wow. He constructs a perpetual motion machine. What does it look like? Well, conveniently, there's a picture right here at the right. See that? Look at that, perpetual motion machine. Of course, you have to neglect gravity, which, is pretty easy to do. Yeah, I'm going to ignore gravity. Without gravity, how would the downhill yesterday look in the Olympics? Beep. Yeah, okay. So sometimes gravity is kind of fun. But don't let gravity bring you down, okay? So what is the perpetual motion machine? It's a weight attached to the end of a long spring that's bouncing up and down. Perpetually. It doesn't stop, right? Doesn't stop. As it bounces, as it goes up and down, as the spring stretches and then compresses and stretches and compresses above its resting position, its distance from the floor, this would be the floor, varies sinusoidally with time, okay? Its distance from the floor varies sinusoidally. The rider sets the spring in motion, okay? So you can imagine the spring is resting. It's just hanging there at its natural length. And he starts this perpetual motion machine in motion by compressing it. Instead of pulling it down and letting it go, he compresses it all the way up to its highest point, which is 60 centimeters above the floor. He's using metric. And then he lets go of it exactly at the same time he starts his stopwatch. Cool beans. 1.8 seconds later, it gets its closest to the floor, 40 centimeters above it. So think about that. He compresses it, he lets it go, and almost 2 seconds goes by before it's all the way stretched down to the bottom. That is a slow-moving spring, isn't it? Yeah, but he built it, so I guess he wanted it to be that way. All right, part A, sketch the graph of the sinusoidal function. You ready? You ready? Did they give us the variables to use in here? They didn't give us variables, so we can kind of come up with our own. We're measuring the distance that the weight is attached to the spring above the floor. So we could call it h again for height if you want. Let's go ahead and set up our axis. Now, just like the problem with the Ferris wheel, the t-axis here represents the floor. It represents the floor. And we're measuring time in seconds. So I'll say t is in seconds. And what do you want to call the function for the height above the floor? You want to call it h for height, or d for distance, or w for weight, or s for spring? Good morning. Oh, okay. All right. All right. Anyone come up with a variable? H. Okay, h. H for height above floor. I like it. So we'll say h of t. It's a function of t. And we're measuring it in centimeters. Centimeters, 100th of a meter. All right, so let's go ahead and set up our vertical axis LSU, which remember is the easier of the two. And let me just draw a whole new line. Snap. There we go. So what is the highest that this weight gets above the floor? 60, right? It says he compresses it to its high point of 60. So to use the majority of my graph, I'm going to come up here and just call that 60. And then do we know what the lowest point above the floor is? Yeah, it says right there, it gets the closest to the floor of 40. So I'm going to call this 40. Now, again, it's not really drawn to scale if you think 0 to 40 and then 40 to 60. So sometimes you might see like 2 slash lines down there. Have you ever seen that? That just means like we're breaking the graph and we're only looking at the top relevant part. So if you want to do that, that's fine. I'm just going to take it away. And then exactly halfway in between 40 and 60 would be the height above floor. If you were just to walk up to the spring before you set it in motion, it would be the natural height above floor that the spring is supporting the weight. So that would be at what point? 50, right? 60 plus 40 is 100. Half of that is 50, so that's the midpoint. And because that's the midpoint, that is also the sinusoidal axis. So we'll draw that down the line. All right, vertical axis all taken care of. Now the fun part, right? The x-axis. Do we know anything about where this thing is at any given time? Yeah, so at t equals 0, do we know where it was at t equals 0? Very good. This is another easy one. This is the math student redeeming himself. Because at t equals 0, he is starting it at a critical value. On the Ferris wheel, he was at a low point, but because he sets this thing in motion by compressing it to a high point, it starts at a high point. So we'll put the mark there. And then it says 1.8 seconds later, it gets its closest to the floor at 40. So I'm just going to come out about right here and call that 1.8. And it says that's the first time then that it's closest to the floor. So what's the significance of 1.8? That's the what cycle number? Quarter cycle, half cycle, full cycle, motorcycle? That's your half cycle, right? It's your half cycle. So we have one more critical value between 0 and 1.8. So let's go ahead and bisect that distance. And what's half of 1.8? You have $1.80 and someone steals half your money. Yeah, you're left with 90 cents, which is not bad. It rounds up to $1, which then you can go to the McDonald's value meal and get a someone stole my money meal, right? You've seen the commercials. No, maybe not. Okay. So where is it going to be at 0.9? 60, 50, 40, or somewhere else? Should be at 50. So let's go ahead and put it out there. So 0.9 is your quarter cycle counting interval now, 0.9 seconds. So now because the distance between 0 and 0.9 on my graph, on your graph, is predetermined, we're going to preserve that distance as we add more critical values. So again, you don't have to measure. You're just going to eyeball it. And I will use my eyeballs also when I'm looking at your graph, okay? As opposed to my knees. I won't be looking at your graph with my knees. That wouldn't work. Okay, so let's just keep adding 0.9 then. And without a calculator, maybe you can help me. 1.8 plus 0.9 is 2.7, and then plus another 0.9, 3.6, and then 4.5. I spy a pattern. Let me move that out of the way. And I got room for one more, so let's go ahead and add it. The next one would be 5.4. Yeah. Oh, I see that. Yeah. The ones place is getting bigger by 1, and the tenths place is getting smaller by 1. Those are just multiples of 9 with a decimal in between. Cool. All right. Do we have at least 5 points marked for one cycle? Yeah, we do. In this case, again, because he started it at t equals 0, we don't need to have any negative values graphed because we're not going to have to extrapolate back in time. All right, so now we just finished our dots. 2.7 is going to be an axis, 3.6 is high, and then 4.5 is axis, 5.4 is low. And with those then in place, we can now connect those dots with our beautiful quarter cycle counting intervals. We'll turn the corner and keep it going. So there is the graph. Do we need to add anything to it? Had to lock the door. I don't want the math getting out. Okay. All right, so that's it, right? We've got our graph. We got at least one cycle. We have our critical values showing. We have our high, our low, and our sinusoidal axis showing and labeled. And we also have the x and y axis labeled. Now, the only thing that's missing is maybe a title to the graph, right? Perpetual motion machine weight distance from the floor sinusoidal graph. I'm not going to write all that. All right, any questions on A, how we did that? Okay, cool. So now it says on part B, I'm guessing, find an equation. So let me go ahead and label this as A. Maybe that was missing. And then part B, I'll do it right below here. So here we go. H of t equals. Now I'm going to try and do it without listing our A, B, C, D, P, R down the left-hand side. Maybe a little bit dangerous. I don't know. With your help, I think we can pull it off. All right, what is the amplitude? 10, right? From 50 to 60 or 50 to 40 is 10. So I'm going to put 10. I don't know. What do you want to use? Plus or minus sine or plus or minus cosine? I don't care. Hey, I'm going to go with positive cosine because that's what y'all said. So positive 10, I'll just leave that awkward space between the equals and the 10. I did leave it open for a negative, but now I'll just keep that as an awkward space, right? Awkward. 10 positive cosine, parenthesis, and let's see. If the half period was 1.8, the full period is 3.6, right? So 3.6 goes in here for B, right? I don't know what I'm doing. Is that right? No, that's P. We need B. Are B and P related? Yeah, they are. Okay. So remember that B is equal to 2 pi over P, just like P is 2 pi over B. So the B value is 2 pi over 3.6. And we can simplify that, right? That's the same as pi over 1.8. Yeah. Now, how does that look to y'all? Are y'all okay with that? Are you okay if someone's trying to talk to you, they talk to you like in a combination of English and Greek? It's like, whoa, pick a language there, buddy. Stick with it. Okay, I'll go with Greek. Okay, now I don't understand a word you're saying. What's wrong with it? Why is this English and Greek? Yeah, it's a fraction and a decimal. That's two different notations for parts of numbers. So let's go ahead and clean that up. And, of course, I'm going to go with fractions over decimals every time. So let's kind of think about how we can do it without a calculator. 1.8 is just one way to read the number 1.8, right? What's the correct way to read 1.8? 1 and 8/10, right? The mixed number, 1 and 8/10, which simplifies to 1 and 4/5. Yeah. And now we can convert that mixed number to an improper fraction, which would be 9/5. Good. 9/5. So really we have pi divided by 9/5. And that's a little bit better because now we have fractions, but now we have a fraction and a fraction. So now we have a complex fraction. So how do we eradicate that? Either multiply by 5 over 5, right? Look them, overlook them. Or you stay, change, flip it, which I'll go ahead and do that here. So you end up with 5 pi ninths. And everyone has to admit that 5 pi ninths looks a lot better than pi over 1.8. It's not an opinion. It's a fact. It looks better. Good. So let's go ahead then and drop 5 pi ninths in right here. 5 pi ninths. So how many cycles now are we going to see between 0 and 2 pi? 5 pi ninths. That's what B is. Good. Okay, do we have a phase shift if we chose positive cosine? Y'all chose it, not me. Nah, we don't need one because, again, at 0, we started at a high point. Now, if you wanted to be like weird and different, of course, you could shift over a full cycle to 3.6, or you can even go to 7.2, or whatever. But we're just going to kind of keep it nice and easy, and we'll put a T there, no phase shift. And do we have a D value? Yeah, what is it? Positive 50, yeah. So much like question 1 on the notes yesterday, this one's pretty easy. Because at T equals 0, we have a critical value, it's a little bit easier. Okay, so now we have our equation. And let's see what else it says. Okay, yeah, part B, find a particular equation. We got it. There are infinitely many others that are correct. Yes? Yeah, so you just got to come up with one. Part C, what is the distance from the floor when the stopwatch would be 10.5? At this time, is it moving away or towards the floor? Okay, well, I guess that means I have to use my equation. And before I use my equation, I'm no fool. I'm going to go ahead and graph that on my calculator in this window and see if I get the same graph. If not, something's wrong. Maybe I'm in degree mode and I catch it. Ooh, that was a close call, a virtual close call. Let me check my mode first. I'm in radian mode. Yeah, that's good. So let's go to y equals, and we'll get rid of all this ugly stuff in here. And we'll type in our equation, which was 10, cosine, and then alpha y equals, to get that pretty horizontal division bar, 5 pi divided by 9. And, of course, on the calculator, we don't use t, we use x. close parentheses, plus 50. Double check, make sure it matches your equation, but for the x instead of the t. And now we go to the window, and we look out and we see if it's raining. No, different window. Our graph goes from 0 to 5.4. So I'm going to go from -1 to 5.4 just to see the y-axis. The scale, if you want to put it to 0.9, because 0 is the critical value, if you put it to 0.9, that's your quarter cycle counting interval, you'll see the critical values. Y-min, again, I'm going to go to -1 so I can see the x-axis. And then something greater than 60, like 65. That'll work. And then for your y-scale, I always turn that to 0 because I don't want to get marks all the way up and down. It makes your y-axis fat. All right, so it looks good. We'll hit graph. And now we can imagine that we're hanging from the weight going up and down the spring. Oh, yeah, fun ride. Does that kind of resemble your picture? Yeah, the only difference is your picture is more awesomer than that one, right? Because you created it. Yeah. All right, so let's go ahead and get a numerical verification, shall we? Let's pick one of our time values other than 0 and see if it matches up with a critical value. Anyone want to throw out a time? 0.9, okay. So at 0.9, we should get a 50 value. So let's go here. We'll hit trace. We'll type in 0.9 and hit enter, and we get 50. So now we know that the calculator is as smart as we, right? Ooh, yeah. Go grammar. Okay, so now we can use it. So now A, B, C comes next. What is the distance from the floor when the stopwatch reads 10.5 seconds? Is 10.5 a t value or an h value? It's a t value. So remember, we show this on part C. We say h of 10.5. Now, I showed you yesterday how to do it from the home screen. You'd have to pick two values, like 10.5 and 10.51 or something. Does our window include 10.5 on our graph? No, I only go to 5.4. So if you want to do it from the graph, and I don't care how you do it, I'm going to go ahead and just stretch that out to 11, and now I'll see more of the graph. And now I can just hit trace, type in 10.5, and I get that. I get the number that I want at the bottom, and now I get a visual, so I don't have to worry about typing in something in the next immediate time. So I write down 3 decimals, 58.66. Do I need that last 0 for 3 decimals? I sure do, because it's part of the accuracy of the number. It's not a terminating 0. And remember, on any final numerical answer, you better put units, right? So what are these units? Centimeters above the ground. And now we're not done. It said at that time, is the weight moving towards or away from the floor? Well, let's go back to the graph. At that time, is it moving away from or towards the floor? Away from the floor. The weight's moving up. So it's moving away from the floor. So we'll say h of 10.5 equals 58.6600, moving away from the floor. You can almost hear the weight say, "Get away from me, floor," as it moves away from it. And the floor's like, "Okay, I'll move away for now, but you'll be coming back to me." Because the floor knows about sinusoidal action. Yeah, okay. You see how you can make these boring problems fun just with a little stupid imagination? Okay. Any comments or questions about part C? Did we answer everything? It's kind of a long question. I think so. Part D. What is the first positive value of time when the weight is 47 above the floor? All right, so 47, is that a T or an H value? It's an H. So on part D, we'll say H of T equals 47. And you don't have to put centimeters there. That's not your final answer. Now, remember, it's going to hit 47 infinitely many times. It is, after all, a perpetual motion machine. It's going to hit on the way up and the way down, the way up and the way down. So we want to make sure that we read carefully and find the correct one that I'm asking. What is the first positive value where it's at 47? So we don't care if it's going up or down. We just want to know what is the first time after he starts his stopwatch where it's at 47. So if you go to the graph, it starts at 60, right? So it's going to hit 47 for the first time somewhere in here on the way down. So what do? We just trace, and we scroll over until the Y values are close to 47. Oops, I'm way over there. Let's actually hit 0. And now I can trace. And I'm going to just scroll until my Y values are close to 47. That looks close enough. So we write down 1.090. Is that how we do it? No. But we know the answer is around 1.090. The way we do it, remember, is we actually come down here to Y2. We graph 47. And now we got a visual. There it is. It's the point of intersection. Second trace number what? 5. Okay, so enter, enter. And now for your guess, you got to make sure you scroll to the one you want. Boom, right there, enter. And ooh, yeah, there it is. So now underneath h of t, we put t equals 1.074 or 0.75 if you're a rounder. And of course, that's your final numeric answer. So what units go at the end of there? Decades? Seconds. Yeah, good, seconds. So SEC is an appropriate abbreviation for both the Southeast Conference and seconds. Okay. Did we finish answering that question? Yeah, we sure did. Part E. Part E1, I should say. Because look, there's 2 E's. It is the most common vowel. During the first 9 seconds, for how long is the weight at least 53 centimeters above the floor? Ooh. During the first 9 seconds, how many seconds is the weight at least 53 centimeters above the floor? So let's go ahead and see if we can interpret that inequality. We want to know where h of t is at least 53. So is that going to be equals 53, greater than 53, less than 53, greater than or equal to 53, less than or equal to 53, or something else? Yeah, greater than or equal to. So I don't care if you put h of t is greater than or equal to 53, or if you put h of t equals 53. I don't care which one. You do need to know where it's equal to 53. So if you wanted to put equals there, I get it. So kind of like we did yesterday, we'll just change 47 to 53, and we'll graph it. But now before we graph it, I'm going to do something different here. Remember, we're measuring time on the x-axis. So I'm going to go ahead and leave that at negative 0.2, but it says during the first 9 seconds, so I'm going to change my upper bound to 9. I don't want to look past the first 9 seconds and be tempted by other values, right? If you don't want to eat donuts, don't walk into the donut shop, okay? There's the first 9 seconds. Okay. I want to know where it's above the red line. So notice it's above the red line for a complete cycle here and another complete cycle here. But then notice it's also above that for just a little bit from when we started. What's our plan of action then to figure out the combined amount of time? Not divide by 2, but double it, right? Because there's 2 of them. Yeah. Yeah. Is this necessarily a perfect half? Very good. It is a perfect half because it starts at 0. In general, if it wasn't a perfect half, being starting at 0, you could just find that point of intersection. So you have a couple of options here. Because this lobe is a perfect half, you could just find this value here, which would give you the duration in its half, and multiply it by 1, 2, 3, 4, 5 halves, right? You could do that. That would probably be the most efficient way. The other way to do it is you could find both of these points of intersection like we did yesterday, subtract them to find the total length, double that, and then add it to half of that number. So being the most efficient, and sometimes you have a little game plan here, I'll go ahead and just find this point of intersection and multiply it by 5, okay? Now we can only do that because this is a perfect half. If this had been shifted over, you would have to actually find both of these and then add it to whatever that value is right there. So let's go ahead and find that first point of intersection. Second trace, number 5, enter, enter, and now I'm going to scroll over here. Sometimes it's fun, like I mentioned earlier, when it says guess. It's kind of like inviting you to guess. So I scrolled over to 0.71. I'm going to guess 0.72 as I hit enter. I guessed. Well, it's 0.725, so it's pretty close. So now on my paper, I'm going to write t equals 0. Dang, I have a bad short-term memory. What was it? 0.725. 0.725. So I do want you to write that down, seconds. And now we're going to do something with it. Let me shrink all that down. So the total time in the first 9 seconds above 53 centimeters is 5 times 0.725 ... What does that mean? Yeah, that I'm not going to use the number 0.725, but rather the full answer. Okay, so because I'm not finding two values, remember the calculator automatically stores that as x. So if you just want to hit x, there it is with all the decimals, you could just hit 5x. And there's your answer. But remember, as we did yesterday, if you had to find 2 points of intersection, so you'd subtract them, you're going to want to hit x, stow, as alpha A. So that when you find the next one and it gets overridden, you still have this one. And if you did store it as A, then on your paper up here when you put t equals, you're going to want to do that as A. And then, of course, you could show me your work by just saying 5 times A, which would be the same thing. So in the end, our final answer is 5 times A, which we already have. It's 3.627 seconds. So at this point, our final answer, we report 3 decimals, but remember, that came from using a stored value and not a rounded answer. So if you have any other answer besides 3.627, it's going to be wrong. 3.626, 3.628. Let's see what you would get if you just did 0.725 times 5. You would get 3.625. Would that be correct? No, because 3.625 is not 3.627. So there you go. There's a perfect example of why you never want to use a rounded number or a truncated number for a subsequent calculation. So if you ever think that you're going to need a number, store it. Store it as A, store it as B. You have the whole alphabet, right, on the front of your calculator screen. So you could store it as any of those variables and then mark it on your paper. Okay, so there you go. So now we're on to part E, the second E. If the writer's little sister, oh my gosh, the little sister, started the machine when the writer was at the yogurt shop. This is so random. He's now at the yogurt shop. So he set up his machine. He's like, you know what, before I start this, I'm going to celebrate. I'm going to go to, what is it called? Wildflowers? What's the yogurt shop? Where like an ounce of yogurt costs $52. What is it? You can add gummy bears to it. What's it called? Orange Leaf. There you go. So the writer goes to Orange Leaf to celebrate, and he's, I'm going to eat this, and I'm going to go home and start that perpetual motion machine. And little sister wanders in, and she's like, ooh, a perpetual motion machine. The writer came home and happened upon the machine that was now already in motion. Is he going to yell at his little sister? Nah, he's a good big brother. He actually brought her some melted yogurt home for her to drink. He's a good student, so he's like, you know what, little sis, I got this. I could fix it. I'm not going to stop it because it's already in motion, but I could fix this. If he then, as it was moving, started his stopwatch when the weight was 51 centimeters above the floor and moving away from the floor, that means it's moving up or down? Up. What would his new equation be? So very similar to example 2 that we did yesterday. All we need to do now on part E2, we'll say, is take h of t and set it equal to what? 51. Yeah, 51. All right, so let's go ahead and do that. We'll come down here and change 53 to 51. And let me go ahead and change my window. Let's go back from 9 let's just put it at 10. I don't know. I'll change it. We didn't need to change it, but it was kind of fun to do so. Okay, now it doesn't matter which cycle. That thing's going to go up and down, up and down, up and down. He catches it when it's 51 and moving, what do we say, up or down? Up. So here's 51 for the first time, moving up, but maybe that's not the one he caught. Maybe he caught this one, or maybe he caught the next one. It doesn't really matter because it's going to be the same equation. So for simplicity, let's just use the first instance that we see, the first positive instance where it's at 51 and moving up. So we want to find that point of intersection right there. So second trace, number 5, and then enter, scroll back to that one? No. That one? Yeah, enter. And it's 2.757. So on my paper, I'm going to put t equals 2.757. So what are we going to do with that number? We want that value right there to be the new y-axis. I want that to correspond with 0. So I need to pick up that graph and move it to the left, right? Left, right? Left, right? Who's marching now? We want to move it to the left, correct? Yes, okay. So to do that, in the equation, are we going to add 2.757 or subtract it? We're going to add it, right? It's going to be plus 2.757. Because we came in late, we have to add time. So remember, if it's plus 2.757 in your equation, that moves the graph to the left. So just like we did yesterday, 2.757, all we have to do is add that to our original equation. So if I take this guy here and copy it, copy, paste it, let me go ahead and just remodel in here, take my scissors and move this over, and I'll say 2 plus 2.757, and then I guess I can get rid of that and move this in closer. And that should move the graph to the left, so that corresponds with the y-axis. Now, as we also said yesterday, let's go ahead and come up with another equation. Let's go ahead and start at 0.9. Let's write another equivalent equation. So another equivalent equation, which I guess we should have done in part B, that would be a what? A positive or a negative sine or cosine if we start at 0.9? That's on the axis moving down, so it would be a negative sign. So that could be negative 10 sine of 5 pi ninths times t minus 0.9, close, plus 50. So what if your equation already has a c value to it? How would you adjust it then if you had to shift it left 2.757 units? Well, you do the same thing. You just add it to it. So the other new equation could be negative 10 times sine of 5 pi ninths times, and let me see if I can squeeze this in here. We have t minus 0.9 already. All we got to do is add 2.757 to it, plus 50. And that should give you the exact same graph. I'll prove it to you, all right? Let us verify. We'll go to y equals. We'll get rid of this 51 because we don't need it there anymore. I'm going to come up here and adjust my graph, second insert, parentheses, and now x second insert plus 2.757. Close it, and it's already closed. So there's one equivalent equation. Let's go ahead and type in negative 10 sine of 5 pi ninths. I'm not going to bother with the horizontal division bar here. 5 pi ninths, parentheses, x, and I'm not even going to add them together first. I'm just going to add them in the equation. So minus 0.9, and then plus 2.757. Close it, plus 50. So now if I graph both of those, and they are in fact equal, they should trace right on top of each other. And both of them should have 51 moving up as their y-intercept. Yes, yes? Yes, yes. All right, here we go. Ready? Ooh. Ah. Yeah. And now we hit trace, type in a 0 just to verify, and there it is. You can see now on the y-axis, it's moving up, which is away from the floor, and it's at 51. Yeah, and we talked about that yesterday. Because we are putting a 3-decimal approximation into our equation, so we don't have to write infilling many decimals, it doesn't quite hit 51, but it's close enough and it's good for verification purposes, right? Okay, there we go. So that's a common theme in these types of problems, how to adjust your graph after the fact. Pretty easy. All right, yay, little sister. She made the problem a little more interesting. Any questions about the rider, the little sister, the perpetual motion machine, the Ferris wheel, the Olympics, or sticky buns? What are sticky buns? Are they like honey buns? They could be honey buns. Is a honey bun sticky? Is it a bun? Yeah, so there you go. A honey bun is a sticky bun. How about a cinnamon roll? Some people call those sticky buns. Yeah. What if you're wearing like polyester shorts on a hot summer day? Sticky buns. Okay, any other questions? Cool. Let's see, I don't know how to do the alphabet, A, B, C, D, E, E. So now we have example 1, 2, 3. I guess what should come next? Example 4. Let's see if I know how to count. Hey, there you go. Look at me. I've never really been good with numbers. Okay, Fundy tides. Anyone ever been to Nova Scotia? No one's ever been to Nova Scotia. Really? I haven't either. Okay. In Nova Scotia, you have Fundy Bay. Anyone ever heard of Fundy Bay? It's where things can get stranded pretty easily. Let's see if we can find, well, instead of Fundy Bay, let me just type in Fundy tides. The Bay of Fundy, it's not called Fundy Bay, it's called the Bay of Fundy. It uses the passive voice. The Bay of Fundy is a bay, it's an inlet with water, but it is renowned for having the highest tide differential in the entire world, okay? Which means high tide and low tide, it differs so dramatically, and we're going to see how much that difference is. So here's a picture on the bottom of high tide. When the tide rolls in, you see the ships there, they are actually afloat. They have water beneath them. But then the tide rolls out, and look what happens in the picture above. There's so much water that rolls out that the boats become landlocked for a little while until the tide rolls in. So it's pretty dramatic, and that happens every so many hours, which we're going to talk about right now. You can actually go to the Bay of Fundy and sit there on the bay, on the dock by the bay, listening to Otis Redding perhaps, and you can actually watch the tides roll in and the tides roll out, and then you could take pictures and put them on the internet so that math teachers somewhere could access them. Yeah, you could do that. So if you ever go to Nova Scotia, the Bay of Fundy is a must-see. If you ever go to the moon, I would recommend the Barrow Crater. Okay, so just some travel tips from me. Let's go ahead and take a look at this example and see if we can get kind of through at least the gist of it. If we don't finish it, it's no big deal. Hey, look, there's the Bay of Fundy right there. Okay, that's in Nova Scotia. The Bay of Fundy in Nova Scotia is known for having the highest tidal range in the world, approximately every 6 hours and 14 minutes. Wow. The high tide and the low tide switch, with a difference of, and this is going to astound you, with a difference of 55.8 feet. That's huge. That's like a tsunami coming in and a tsunami going out. In between, I don't use exclamation points that often in my writing, but I had to use one here. Yeah. If we assume that on any particular day, we were there virtually, we observed the low tide at 8:45 a.m. Sketch the graph of the tides in feet for that entire 24-hour day. We're measuring time in minutes after midnight. Ooh. Assume a sinusoidal axis is at y equals 0. Okay? So we're going to let y equals 0 be kind of like sea level, and it's going to rise above and below 0. All right, so if we're going to sketch the graph, T equals 0 corresponds with what time? 12 a.m. Midnight, right? Midnight. And we're measuring time in minutes. So let me extend that. We're measuring time in minutes. All right, so now I actually kind of drew it wrong. Let me scoot that down. Because T equals 0 is the x-axis, and we're going to call that y equals 0, the kind of sea level. If the tide differential is 58, or 55.8, is 55.8 going to be the amplitude? Right, half of that. So let's see what half of that is. We're not going to be able to finish this, but I think we'll get the essence done. So 55.8, let's go ahead and divide that by 2. So 27.9. So now we know that it's going to go up to 27.9 and down to negative 27.9. So for the first time, we have negative values. What do the negative values now mean? If we have a negative value, that means that the tide is in ebb. Okay, it's in the receding. Could still be going out, still be coming in. See y'all later. All right, so there's the y-axis. We've got it set up. Now we have to see where we are at a given time. It says that we observed the low tide at 8:45 a.m. Holy moly smokers. We're going to need a sacrificial axis. Here's 0. Here's 8:45 a.m. This is 12 a.m. Remember, we're measuring in minutes. So we need to figure out how many minutes after midnight 8:45 is, right? How are we going to do that? Well, 8 hours after midnight is 8 times what? Minutes in an hour? 60 plus the 45. So 8:45 corresponds with 525 minutes. Do we know what the do we know what the period is? Is 6 hours 14 minutes the period? 24 hours is the period? Well, let's see. Every 6 hours 14 minutes, the high and the low tide switch, so it goes from high to low. So that's a half of the period, right? So times 2 is the full period. So the full period is 12 hours, 28 minutes. 12 hours, 28 minutes, which we need to convert that also to minutos. See? So let's do the same thing. 12 times 60 minutes plus the 28. 748. Sweet, sweet, sweet. So the period is 748. Now, here's another way to get your quarter cycle counting interval. We've been like graphing it and then bisecting it and bisecting it. But for the first time, we have a low tide at a value that is not necessarily a critical value based on 0. So here's another way to figure out your quarter cycle counting interval. Take your period and divide it by 4. Yeah. So let's take 748 and divide it by 4. So that's 187. So now we have the most important number on the entire Bay of Fundy. So let's go ahead and see if this is a low tide. I'm going to call that L. Let's work back from 525 because we need to work back towards the y-axis. So 525 minus 187. 338. I'm going to add that to my sacrificial x-axis, 338. Okay? So that's also a critical value. Let's do it again. Let's subtract 187. That gives me 151. So 151 is also a critical value. Let's do it again. Remember on the calculator, if you do something twice, it remembers it. So if you subtract again, you're at negative 36. I like that. I'm going to put negative 36 right there. And then I'm going to move my y-axis over to somewhere in there. So here's the cool part. Now with our sacrificial x-axis ready to go, I can go to my final graph. Negative 36 is a critical value. I'm going to draw that pretty close to the y-axis. 151 is the next critical value. It's going to be roughly 5 times further than that distance. Okay, so we're not going to finish, but here's what we would do. When we make our final graph, here's negative 36, and then I'm going to come out way over here and call that 151. And now this distance here is what I need to try to preserve as I make my new critical values, something like that. Now we can also figure out what that critical value is. If this is a low point, then 338 is an axis point, 158 is a high point, yeah? Working backwards. So now you can actually put a high point here. This would be an axis point. This would be another axis point. And then this would be a low point. So that is how you get your graph when 0 is not a critical value. And that's all we have time for, but that's all we really need. Because once you have the graph, we know how to write the equation. Once we have the equation, we know how to answer questions. Okay? So that is the essence of the Bay of Fundy. We are done with this section. Homework's due tomorrow. Tomorrow in class, you'll work a practice test. And then Friday's the big fun party. All right. Enjoy the rest of your sticky buns day. And having said that, I hope you're able to get out of your chair today to go to your next class. All right.